Okay, I'm happy to introduce Chen Chen, who's talking about HORNET.
Okay, thanks for the introduction. Hello, everyone. I'm Chen Chen from Carnegie Mellon University. So today I'm going to present HORNET, high-speed onion routing at the network layer. So this is a joint work with my colleague, Daniele Assoni, David Barrera, my advisor, Adrian Perrig, and my collaborator, George Danensis. So to start with, so I think you have seen enough evidence about domestic and international mass surveillance. Today, government is investing a lot of resources trying to conduct this mass surveillance program. So, however, a lot of users do care about their anonymity, and as a countermeasure, so more and more users begin to adopt anonymity networks such as Tor or I2P. So take Tor as an example. The figure in the red shows the average number of daily users between January 2015 and March 2015. We can see that number is about 2 million. So even though that absolute number is pretty huge, given the total amount of internet population, the coverage rate is still low. So why is that, and how can we improve? One of the reasons could be that a connection through Tor is simply slower compared to a connection without onion routing protection. First, today's Tor is constructed as an overlay network. So a link between two neighboring nodes can traverse the entire internet. And this adds a lot of propagation latency. Second, so onion routers today are usually operated by end hosts, which are operated by volunteers. And their throughput are usually lower than 100 megabytes per second. So if you compare this with commodity onion routers operated by the ISP, so this is pretty small throughput. So in this work, we propose to move onion routing scheme into the network layer for higher throughput and lower latency. Our vision is that future network routers can provide onion routing capabilities. For example, for each flow between the source and destination, we assume that the autonomous systems on the path can negotiate a key with the source and then use this key to onion encrypt or decrypt data. So compared to today's Tor on the overlay network, which usually use long and zigzag paths, an onion routing protocol in the network layer will be able to use shorter paths and more direct paths. In addition, compared to the end host, which usually has limited throughput, network routers can provide much higher throughput. So there are already existing proposals that propose to implement anonymous networks at the network layer. So among them are Lab and Dovetail. They offer high throughput. There are evidence in the paper showing that their speed is faster. However, compared to today's state-of-the-art Tor, so they offer weaker security guarantees. For example, when the packets traverse the network in Lab and Dovetail, the packet doesn't change. So this allows easy matching, flow matching based on bit patterns. Second, so these packets in these two proposals will leak information about the path. For example, how many nodes between the source and destination, or a router's position on the path between the source and destination. So if we put all this scheme in scope, and if we put security in x-axis and throughput in y-axis, so today's Tor and I2P provide higher security but lower throughput. And lab and dovetail, they provide higher throughput, but only a weaker security guarantee. So our goal is to achieve the best of both worlds. So we want better throughput and better security guarantees. However, like designing a network layer onion routing protocol is not to directly adopt today's Tor design. Why is that? So we observed that Tor design suffers from scalability at the network layer. So in today's Tor design, each onion router will keep state for a circuit that traverses that router. This state may include onion keys, the information to find next hops, or pointers and flags. So how much is that state if we let a router actually runs this protocol? So we simulate the amount of state needed by using traffic trace data from KDA backbone router. So we calculate the amount of state that required to store by each router. So in fact, so for a router with 100 gigabits per second throughput, a Tor node demands around 20 gigabytes state to be stored. So this will overwhelm the current small high-speed memory on today's routers. So in the next slides, I will present HORNET. It is a scalable high-speed onion routing protocol at the network layer. So HORNET is capable of achieving high throughput that is comparable to today's backbone routers. And to solve scalability problem, HORNET will require no peripheral state on each router. And finally, HORNET is probably equivalent to an ideal onion routing protocol defined by the research community. And I will elaborate more. Okay, so here is an overview of how to achieve sender anonymity in HORNET. So the communication in HORNET is still session-based. There are two phases in each session, a setup phase and a data transmission phase. Like Tor, in each setup phase, a router will negotiate a symmetric key with the source using Diffie-Hellman key exchange protocol. To reduce the latency introduced, compared to Tor's telescopic way of negotiating keys, HORNET only uses two setup packets to traverse every node in the single round-trip time. Later in the data transmission phase, so the router can then use the symmetric keys set up in the previous phase to support fast packet processing. Okay? So to achieve scalability, HORNET leverages a state offloading technique. In general, in the setup phase, instead of storing the state locally, each router will insert its state into the setup packets, and the source will collect those states from all nodes from setup packets. In the data transmission phase, each router will require the state to process the data. For example, the onion keys is in the state. So in order to onion encrypt or decrypt the data, the key is required. So in this case, the source will embed state into each data packet, and each node will retrieve the state from the packet header and then use the state to process the packet. So, however, the technique is easier said than done. There are two major challenges when putting state into packets. First, so the secrecy and the integrity of the state has to be protected. For example, if we don't protect the secrecy, an adversary who gets access to the onion keys will be able to reverse the onion encryption or decryption performed by that node. So in HORNET, so the state is protected by a pseudo-random permutation keyed with a local secret value SV of each router. So the secret value SV is really shared among all the circuits traversing that router so it's not a per circuit state. And since this secret value SV is local and only known to that router, so the state is only accessible by that router. So second, so when we consider the state from all nodes put together, so they form a path. We also need to protect the information of that path. For example, in lab and dovetail, so you can look at the packet header and decide how many nodes are between the source and destinations. Or you can, when a node processes the header, so in lab and dovetail, they know like their position on the path. So we call this information path information, and leaking this path information can lead to de-anonymization techniques. So in order to protect this path information, we propose two data structures. In the setup phase, HORNET uses FS payload, and in the data transmission phase, HORNET uses anonymous header. So let me explain these two data structures in the following slides. So both of these two data structures are unencrypted data structure. Their tasks are to contain the foreign segments. And their functions are complementary. Remember, the source will need to collect foreign segments in the setup phase. That is done by the FS payload. And in the transmission phase, each data packet will contain the state for each node. So that is done by anonymous header. To give you a flavor of how these two data structures work, so let me first use FS payload operation as an example. Recall that each node will insert its foreign segments into FS payload in the packet during the setup phase. The operation used here is called addFS. Here, let us assume node 0 will insert its FS0 into the FS payload by using addFS operation. So the input FS payload is filled with padding bit first. And then node 0 will prepend its FS0 at the head of the FS payload. After that, the FS payload is cut to appropriate size. And finally, the resulting FS payload is encrypted and the MAC is prepended again at the beginning. So I would like to point out two observations about the operation here. First, in addFS, processing only happens at the head of the data structure. So therefore, performing the operation will not require or leak information about a node's position on the path. Second, both the input and output of FS payload are of the same size. Therefore, processing these data structures will not leak the information about number of nodes between the source and destination. So then let's see how anonymous header operation work. Here I will use getFS as an example. GetFS is used by a node to retrieve its state from the packet header. So again, we assume node 0 would like to retrieve the state from data packet. So you can see the process is very symmetric to the addFS. In fact, it's the reverse of it. So node 0 first will obtain FS0 and the MAC 0 from the head, from the beginning of the packet header. And then it will decrypt FS0 first, retrieve its onion keys, verify the MAC checks, so the header is really not modified. And then it will pad the header to the right size, and then do a decryption over the header. So again, like if you think about these two observations, so it still holds here. Therefore, neither of these operations can leak path information to a node who process it, or the root tree who just monitor the link. Okay, so up till now, so I have shown you how the necessary data structures for offloading state works. So now together, let's look at how the process actually works in the setup phase and in the data transmission phase. So in the setup phase, HORNET relies on another probably secure onion routing protocol called Sphinx. So Sphinx helps HORNET to set up per session state, including the onion keys. However, we cannot use Sphinx for the entire process. That is because processing a Sphinx packet requires Diffie-Hellman key operation, which is very slow and cannot support high throughput. So each Sphinx packet contains a Sphinx header, which allows the packet to go through the network and negotiate keys with each hop. And also a Sphinx payload, which allows the source to send confidential data to destination. However, to collect foreign segments, each setup packet also have a FS payload, which is the third component in the figure. So at the beginning of the setup phase, the source will create two Sphinx headers, send header and for the forward pass, and the reply header for the backward pass. The source will use the send Sphinx header to send the first packet to destination, and then place the reply header as the Sphinx payload so destination can retrieve it. And finally, it initiates a FS payload in the first setup packets. As the first setup packets traverse the network, each node will generate its own foreign segments and insert it into the FS payload until it reaches destination. Now, destination can create a second Sphinx packet or reply Sphinx packet. This is done by retrieve the reply header from the first packet and put it as the Sphinx header of the second packet. Retrieve all the foreign segments inserted in the first packet and put it as a Sphinx payload so the source can obtain it. And then as the second packets go through the network, until when it reaches source, you can see the packet contains all the foreign segments for every node in the network on the path. So now, as we'll be able to obtain all the foreign segments from the reply packet. So that is the end of the setup phase. Now the source can enter data transmission phase. In data transmission phase, processing a packet only requires symmetric crypto, so there's no more Diffie-Hellman key exchange. Each data packet contains an anonymous header, which led the node to retrieve its state, and the onion payload, which has data and which is onion decrypted and encrypted or decrypted. At the beginning of the data transmission phase, the source creates two anonymous headers, one forward header, which can be used to send data from source to destination, and the backward header, which can be used to send data back to the source. However, at this time point, only the source has these headers. Destination does not yet have the backward header to send data packets back. So to allow that, the source in the first packet will send this backward header as a data payload to a destination. So destination, when obtain this header, can begin to switch data packets. Okay, so that's roughly how sender anonymity works in HORNET. So now let's see how receiver anonymity works based on the sender anonymity protocol. Like Tor and other anonymity networks, HORNET will rely on a rendezvous point to provide receiver anonymity. This rendezvous point could be end host, which are operated by a volunteer, or SP that is willing to support hidden service to for its customer. In Tor, rendezvous points will keep per circuit state that maps an incoming packet from a circuit to its potential destination. In HORNET, we require like the rendezvous point to keep no per session state in case ISP's router operate as a rendezvous point. So the key idea is to allow a nested anonymous header. This means that anonymous header from the sender to the rendezvous point can carry another anonymous header from the rendezvous point to destination. So the figure in below shows how it works. So in order for destination to set up a hidden service, it first selects the rendezvous point and create a session with the rendezvous points. This results two things, a forward anonymous header and a backward anonymous header between the rendezvous point and destination. Now, destination can publish this information to a website, for example, and a source which want to use this hidden service can retrieve that information and know which rendezvous point is serving, and then set up another session between the source and the rendezvous points. Okay, so now the source can already send traffic between source and rendezvous points. So, and what we do is we allow the data packets sent from the source to rendezvous points also contains the anonymous headers from the rendezvous point to to destination. Now, the source and destination can communicate because when the rendezvous points get the packet, it can retrieve the header for the second half. So that's how the data packet will traverse through. Okay, similarly, the destination can use the same trick to send data packets back to the source. So that's a general description about how HORNET works with the state offloading technique. And now let's see some security analysis of the protocol. So according to Kamenisch or Linsetskaya, an onion routing protocol is an ideal onion routing protocol defined in UC framework if and only if it satisfies 4 properties. These are defined in the original paper as like a more formal method. But here I want to just briefly describe these properties. They are correctness, meaning the protocol will execute correctly according to its specification. Integrity, meaning that adversary cannot forge or modify a packet. And wrap resistance, meaning adversary cannot unwrap a packet, unwrap a node's operation. And finally, security, meaning adversary cannot match output packets of a node to the input packet of that node, just by bit patterns. So as limited by time, I cannot show you the full details, but if you're interested in how we prove that, so you can look into our technical report. And finally, I want to point out that HORNET, similar to Tor, HORNET is not protecting against traffic analysis attacks or confirmation attacks. So it's still vulnerable to this traffic analysis and confirmation attacks. So to evaluate HORNET, we implemented on software routers with the support of data plan development kit and AES-NI support. Our testbed contains software routers connected with a packet generator through 12 10 gigabits link. So at maximum, so we can test 120 gigabits per second throughput. And on the software router we use have a Intel Xeon CPU with 2 sockets, 8 cores per socket. And it has also 64 gigabytes memory. So what we want to test is whether this testbed can already support bandwidth throughput high enough for today's backbone routers. Okay, so first I want to show the results of data transmission throughput. In our experiment, the HORNET can achieve 93 gigabits per second with 12 ports and 2 cores per port. And this is comparable to a commodity router throughput. And one of the reasons why HORNET can achieve this fast data forwarding is that today in commodity CPU, the technique like AES-NI can really allow high speed data encryption or decryption of packet. Another reason is that retrieving the state from packet itself remove the requirement to compete for the shared state. This increase parallelism. So we also tested Throughput of HORNET, which is the net throughput excluding the headers. Though HORNET has relatively larger headers because it also contains all the state, it still achieves 74 to 85% of Throughput with of IPv4 with 124 bytes payloads. So this whether it's 74 or to 85% depends on like how many hops between the source and destination. So for different configurations, the mileage may vary. So although both the results and both results are only like from our preliminary implementations, so they have demonstrated that the onion routing is viable for high-speed routers. So next, we test the latency of processing data packets and the setup packets. So the figure in the left shows the latency of processing a data packet with different payload sizes. We have tested and compared with several other related works. So in the figure, x-axis is the payload size, and y-axis is the latency. Lower is better. We can see that processing a HORNET data packet only requires around 2,000 cycles with different payload sizes. So that's roughly 0.75 microseconds, and is almost ignorable given today's propagation latency. And for the setup packets, remember processing setup packets require Diffie-Hellman key exchange, so it's slower. The table on the right shows the latency of processing a setup packets, and it's roughly around 250 microseconds per packet per hop. Even though this number is much larger than processing a data packet, it's only done once for each session. So, and this latency itself is also, I would say, works with today's applications. So to sum up, in this talk, so I have presented HORNET. It's a high-speed onion routing protocol at the network layer. So there are two takeaway messages in the form of question and answers. First, can onion routing protocol achieve high throughput at the network layer? Yes, in this work, we have demonstrated that it is viable for onion routing protocol to achieve high throughput, which is comparable to backbone routers. Second, can we remove the requirement for keeping per circuit state on routers in order to achieve scalability needed by a router? Yes, so we have designed a protocol that requires no per session state on each router, and then we have proof that this protocol is secure under the current framework. So with that, I will end the talk. So thanks.
Any questions? Okay, great. Then thank you very much, Chen Chen.